welcome to the 2018 M-OSRP Annual Technical Review. M-OSRP is about identifying and addressing, prioritizing, pressing seismic exploration and production challenges. That sounds like PAP. For us, it's anything but PAP in our history. We have learned that you need to connect with seismic interpreters and those making drill decisions to know what real challenges are. And that speaking to researchers is an interesting, useful thing, but by itself is not necessarily how you're going to find out what the real problems are with what we deliver on when they work and when they don't work. So that's a controversial statement all by itself, but why waste time? Because, not upsetting someone to do that. One of the things we point out is that if you look at the technical conferences and journals, you see nothing but success. And yet, if you look at the Deepwater Gulf of Mexico frontier drill success rate, it's 1 in 10. It hasn't changed. And so there's a disconnect somehow between what researchers we report and reality of the drill success rate. That disconnect for us is a tremendous opportunity. It means there are issues, and to identify those issues is an opportunity, and we are very grateful for the support we have received for addressing certain of those issues in our history and currently. So why are there challenges? Among the reasons are every method that we have ever used or developed, every method without exception makes assumptions. And when those assumptions are satisfied, the methods can be effective. When the assumptions are not satisfied, the methods can have difficulty and fail, and that can be a contribution to dry hole drilling or suboptimal appraisal or development wells. Not really that complicated. So among the types of assumptions, there are, you have to acquire adequate data for given methods, you have to have adequate compute power, and the innate algorithm assumptions or requirements. What did the algorithm assume when you derived it? What are the prerequisites it requires in order to be effective? So what are you going to do when you identify that an assumption has been violated? Okay? There are two things to do. Remove the violation by satisfying the assumption. Yes? The other is remove the assumption. Yes? So you don't have a violation. We adopt one or the other of these attitudes towards challenges depending on the issue. So for example, reference wave removal and deghosting are, as it says on the bottom of this slide, reference wave identification and removal and ghost removal. For us, that's a prerequisite for every single step in the seismic processing chain that we look at, and we don't know a way to avoid it. We don't know a way to develop methods that don't have that requirement, so we need to find methods to satisfy it. And so that's an example of dealing with a violation by removing the violation and satisfying the requirement. There are other activities within this program, multiple removal, as we know, and depth imaging and Q compensation without Q, where traditional requirements for subsurface information, which we couldn't see a way to adequately provide directly or indirectly for multiple removal in particular, to develop methods that don't have that requirement. So you deal with the violation of the assumption by developing a method that doesn't have that assumption, doesn't have that requirement. If you can do the first, which is find a way to satisfy the assumption, I wholeheartedly support and encourage you to do that. Why? Because most people who work in our profession, if they believe that you need something in order to achieve a certain processing goal, the worst thing they're going to hear is that you don't. You found a method that doesn't need that, because finding that prerequisite is what they're expert at. And so it gets very personal and professional, yes? So if you can find a way to help satisfy a requirement, you'll have a much easier path in life, professionally and otherwise, okay? If you seek to find a method that doesn't require what they think you need, you're going to have a rougher road. Okay? So given all that, speaks again to the huge gratitude and appreciation we have for the support we have had and do have to carry on the kinds of activities we do. So what this slide says is, if a method has a certain prerequisite, we don't say, well, if you had adequate deghosting or adequate reference wave removal or adequate free surface removal or adequate internal multiple removal, then our imaging would work. If the method for new imaging that we pursue, or Q compensation without needing to know Q, if they have prerequisites, we feel it's our responsibility to provide it. It's not some other consortium's responsibility. So here's a processing chain. For the marine case, item 1 says you collected some data in a foam in the ocean, let's say in a total streamer, and these are the steps that in our world data goes through processing steps. And what's interesting, of course, about this this chart or this tree of chain processes is this program, this meeting today is going to take us through what data does. In other words, the first step is you get this recording in the ocean, and the first thing you have there is the reference wave, which is the direct wave, and the wave that hits the air-water boundary, that item on the left, upper left, is identified and separated from reflection data. In other words, everything except reference wave has experienced the Earth. Then the reflection data is deghosted, item 3. Yes? Then once you have deghosted data that doesn't have a reference wave, at that stage we define primaries and multiples. In other words, once the data is deghosted, the deghosted data starts from the source going down, and at the receiver is moving up. That's deghosted data. And it has one or more upward reflection between that down from the source and up at the receiver. Events are cataloged. Reflection events, deghosted reflection events, are cataloged by the number of times they have an upward reflection between the down from the source and the up to the receiver. So if you have a single upward reflection, you call that a primary, no matter where that upward reflection occurs. If there are 2 or more upward reflections, we call that a multiple, and then multiples are then further cataloged by the location of the downward reflection between 2 upward reflections. If there is at least 1 downward reflection at the air-water surface, it's a free surface multiple. Yes? If all the downward reflections are below the air-water surface, it's an internal multiple. So what happens between 3 and 4 is free surface multiples are separated from primaries and internal multiples, and then further, and we have honored and pleased to have Dr. Paulo Carvalho, the pioneer of free surface multiple removal, okay, here with us today from Brazil. So you'll see certain of his activity, and then and how that compares. How does ISS free surface multiple removal, for example, compare to the standard SRME? Yes, plus adaptive. That's become like tissues and Kleenex. Well, what is SRME? When is it the appropriate tool? And when should you consider ISS free surface? Okay, there's a talk on that. So then you have primaries and internal multiples, and then internal multiples are attenuated and then eliminated with a sequence of ever more capable methods. The yellow dots mean they're inverse scattering series, meaning those steps are achieved without subsurface information. The green dots are Green's theorem. For those wave separation methods, separating reference from reflection data and separating ghosts from non-ghosted, those do not require subsurface information at all, but Green's theorem is adequate to remove them. And then we have processes on primaries. Once we have primaries on their own, and one of the new activities here is an ISS subseries that produces a data without Q. In other words, a data as though it never experienced absorption dispersion in the subsurface without knowing the mechanism. In goes the data, out comes another data. Just like Cavallo's, in goes the data with free surface multiples, out comes the data without free surface multiples. No subsurface information. It's exactly the same thinking, okay? Over and over again, all those yellow dots. Okay, so we're going to start, as I said, the order of the presentations in this meeting is going to follow this chart. And so the first presentation by Dr. Jing Wu, recent alumni at Schlumberger, we're honored that she would come and speak to us today, will be about that item 2. In other words, separating both reference wave from reflection data and then having reflection data and removing ghosts, okay? So this is, I basically went through this. I'm saying we're in the middle of this introduction, and then Dr. Jing Wu is going to tell us about Green's theorem methods for preprocessing, meaning reference waves separated from scattered, and deghosting for offshore and onshore. Recent progress on that, okay? And then there's a talk by myself on multiples, a new comprehensive perspective on primaries and multiples, incorporating the removal and usage of multiples. In other words, before we go into a whole set of talks on inverse scattering series and free surface multiple, internal multiple, we need to remind ourselves, why do you need multiples removed? And what is this activity about using multiples? Yes? It turns out that the people who are removing multiples and the people who are using multiples are after exactly the same goal. Okay? The goal is primaries. If we had a complete set of primaries, multiples have no use. Okay? The reason that multiples have a use is there are certain unrecorded primaries whose image you'd like to have. Yes? And so when you'll see that to use recorded primaries, you need to remove recorded multiples. And to go after an unrecorded primary as a sub-event of a multiple, yes, you need to remove unrecorded multiples. So you are in the multiple removal business, whether you are after recorded or unrecorded. They are not adversarial. It's very catchy for workshops to say, do we need to remove them or should we use them, yes? Or migrate them. First of all, migrate multiple is absolutely nonsense. That word, you'll see, it has no meaning. It's marketing, okay? And multiples are not the new primary, okay? They're not some rehabilitated primary. They have use if there's a primary that's missing, okay? It's a primary that's missing that gives a multiple at times some use. If the multiple itself has no sub-event that's unrecorded, the only interest is remove it. Even if you use it to get after a sub-event that's unrecorded, that's a primary. After you finish using it, you need to remove it because that recorded multiple is going to affect imaging of recorded primaries. So there's a lot of miscommunication. So in our view, the removal of multiples and using of multiples are complementary. They're not adversarial, okay? They're after as much of a complete set of primaries as we can achieve, because primaries are what we image and invert, okay? Any questions on that? So by the end of the meeting, if anyone doesn't feel upset, Please let me know if you feel ignored, okay? We do our best. In other words, if you walk in here and walk out comfortable, then there's nothing you've heard new. And Bob Stolt, my colleague for many years and still, he once said, Art, let's only say something if we got something to say. I said, well, that's a tremendous disadvantage, you know. Most people just sort of cosmetic, more small changes, you know, everybody's comfortable, we keep on going, okay? So, this talk on multiples is a new comprehensive view with a new migration method, is to explain why we're removing them. Why are you removing them? Then after you know why we're needing to remove them today, then we'll go on to how do we remove them. Free surface and internal, attenuate, eliminate, yes? We have to remind ourselves why, yes? And why we, in this group, focus on removal. Why don't we focus on using? We'll explain that, yes? Do we feel those who are using, like our colleagues at PGS, are doing something valuable? Do we think that should be encouraged? Absolutely. Why do we have a certain priority here? Yes? That needs to be communicated. So then there's an ISS tutorial, which then of course leads to a set of talks on free surface multiple, the SRME plus adaptive, compared to the Carvalho et al. ISS free surface. When should each be the appropriate choice within your toolbox, yes? Then Yang-Li-Zhou et al. Will show a multi-dimensional internal multiple elimination method that produces the exact time and exact amplitude of the internal multiple. The current method that you're using, if you are using a service by CGG, PGS, TGS, Schlumberger, you're using the ISS internal multiple attenuator. Yes, they've given full credit to where that originates. The attenuator produces the precise time and approximate amplitude of the internal multiple. It's an attenuator. So if you need to remove a multiple, you need to do an adaptive subtraction to just, that adaptive subtraction step assumes the multiple is isolated. If you got somebody in the neighborhood, you can damage a target primary, yes? So that's for isolated internal multiples, that issue for us is solved. In other words, it's ISS internal multiple attenuate, no subsurface information, plus adaptive subtraction, yes? The open issue is when they interfere or they're close, yes? And the adaptive can damage things you don't want. That's when you need a stronger prediction, yes? And that's what Dr. Yang-Li-Zhou, Chao Ma et al. Are providing. An eliminator, something which surgically removes that multiple, yes? And when you need it when you have proximal or interfering. If you don't know, then you probably should use it. It's the same with the earlier Chao Ma, Chong Fu et al. Talk on free surface. If you have a free surface multiple, which is isolated, then SRME plus adaptive is fine. Because the adaptive is going to fix up all the things that SRME doesn't produce in the right amplitude and time. If, however, you have an interfering or proximal free surface multiple to an event that you'd rather not have damaged, then we suggest the ISS free surface algorithm, which will surgically remove that multiple and doesn't call upon, in principle, an adaptive subtraction. Okay? So it's a toolbox issue. Okay, then it's natural enough that we would look for how are these different algorithms work in different Earth model types. And Dr. Jingwu has led us into the world of absorptive dispersive. There's a paper in 2003 by myself and colleagues where we proved that the ISS internal multiple attenuator, and Paolo is an author of that paper, the ISS internal multiple attenuator is model type independent. In other words, one same unchanged algorithm not only doesn't care about subsurface information, it doesn't care whether the Earth is acoustic, elastic, anisotropic, and elastic. The algorithm doesn't change. Well, that's a nice theory, but then how could you show an example in anelastic where that predict the right time and approximate amplitude works? So Jingwu's talk this looks at that with analytic data. In other words, the data is perfect. So the issue is the algorithm. If you see a result that's not what you amplitude or phase not what you expect, you can't blame the data. You blame what we produced. And then following ISS attenuate, of course, the next talk is Cheng-Fu et al., Yang Lizhou, Jingwu, on what about the internal multiple eliminator? Yes, in the presence of absorptive dispersive. Yes. Then we at 3:30 today, Dr. Yang Lizhou will give a talk on this a new ISS subseries that does Q compensation without needing to know, estimate, or determine Q, and without needing low frequency, and in particular without needing zero frequency. There's earlier work from this group with Chris Innanen, Jose Eduardo Lira, and myself, which had an ISS Q without Q subseries. Yes, the reason that was not progressed is it needed zero frequency data. Yes, and so there's a new subseries which avoids that need. Okay, totally avoids it. That advance has tremendous consequence for all amplitude analysis. If you are doing FWI or any other kind of amplitude analysis, and to get low vertical wave number, you need low frequency. What this is doing says you don't need to. You can reformulate it so that you do not need low frequency to get that jump. You understand? That box. You understand that first step? So there are also consequences for electromagnetic. In electromagnetic theory, the role of Q is conductivity. So the Q without Q subseries can be turned into a Q estimation. So this is a method to produce Q. Yes, can be turned into that, or in the electromagnetic case, produce conductivity map. A new way to conductivity map is very interesting for oil-gas separation. Yes, so that's today, and then tomorrow we're going to talk. In other words, we've taken you through multiple removal and different issues with it, different types of multiples. Now I'll have a few words about a new method for migration. The industry standard RTM, industry standard migration RTM, and extensions of RTM by Bleistein, Yu Zhang, yes, Sheng Zhu. All of those methods, okay, we will show are high frequency approximations. They are intrinsically high frequency. It doesn't matter how you implement it. The imaging condition is a high frequency approximation. That means it's treating high frequency more accurate than low frequency. So if we get broader band data, more low frequency, will RTM benefit from it? Yes, it will, but not as much as it would if it was not a high frequency approximation. So we've developed a migration method that we call Stoltz C3 for heterogeneous media. C is for Claerbout, yes, based on Claerbout's third imaging principle, that is equally effective at all frequency, yes, and hence can deliver full benefit from the lower frequencies that you would require, even if you have one bandwidth. You don't have to get lower frequency for that to have value. For a given bandwidth, you'll see that that's not well known. If you say Kirchhoff is high frequency, everybody says, I got it. You say RTM is high frequency, with all that big building and all that computers, you're telling me it's high frequency? It is. Okay, so one thing is we can't just say it. How do you show that? Yes? We'll show you that, yes? And so then what we're saying is, we're suggesting you might look at another way to migrate. That's with a velocity, yes? That's a traditional migration, yes, with a velocity that could provide value. And then Chung will talk about how do we arrange that for, first you'll see resolution differences for a reflector and a wedge, yes, between RTM and Stolz C3, where there is a width of a reflector of a layer that RTM thinks is a reflector, yes, and Stolz C3 sees it as a layer. You know, that's resolution difference. Okay, that's a reservoir identifier difference. Yes, that's what you'll see. And then when you implement this in heterogeneous media, how do you know that this numerical method that you use to implement it will be equally effective at all frequencies? Not just the imaging condition, you do some numerics. We have a way to have control that the numerics are providing the propagation part of migration, retaining the resolution value of RTM for RTM and for Stolz C3, that the heterogeneous doesn't add an issue. Yes? With numerics, how are you going to, that was a big headache for me. How are you going to figure this out that you don't ruin things once you do heterogeneous? So there's a method, and that will be discussed. And then we'll have a tutorial tomorrow showing how everything we do here can be derived from one single point. See, if you do things like we do that are counterintuitive, that people think don't make sense, how can you do this without information? It's incumbent on us to be as clear as possible, yes? Not just increase the volume, provide a logic, yes? And provide a starting point and a set of logical steps that if people have a difference of view about that, they can say, that first step, oh, I don't agree. Or I accept that, but there's some step between that and that algorithm that doesn't need information that I have an issue with. Then we can have a discussion, yes? But it's incumbent on us to be clear. If we're doing RTM or FWI, we don't have to worry about it. We're all in the room, agree already what we're all about. You understand? If you're saying something that's not conventional, it's incumbent on whoever communicates about such a thing to make it clear. Yes? Okay. So with that, we'll, well, I guess this talk never ends. Okay, so what I'm doing now is a prep for Jingwu, who's going to be talking about preprocessing. So I'm going to give a quick introduction to how Green's theorem is used for preprocessing steps. Okay, so the first, what we're basically interested in is a wave. There's a seismic wave, and it's generated, and it's affected by its environment, what it propagates through, what it comes out. Okay, so we are interested in descriptions between the source and the environment and the wave. Why? Because ultimately we want to extract from the wave certain of its experiences, yes? Certain of the things that it engaged with. We want to identify them. How? By the way that environment affected the wave's character, we want to understand the environment, yes? So we need a mathematical relationship. So let me just, please listen to this, what I'm going to say. There are many different ways to describe what I just said. A wave and what generates it and what it experiences. The model that we're going to use, not because it's the only model that we find useful for certain applications, is the following. Assume the world has some reference medium, yes? Could be homogeneous, in some cases it won't be, you'll see. But some reference medium. Then everything that's not in the reference medium you described, that's reality. The air guns, the heterogeneities, yes? Anything that's in the real world that's not in your reference is to be considered sources. Sources of waves that originate by the difference between reference and what's really there. Okay? And so that picture we find useful for several different applications. So it doesn't talk about the wave directly caring about the actual properties. For example, finite difference, finite element. You generate a wave directly in terms of actual properties. Velocities, densities. It's not a reference and then you add something on, yes? And we certainly see the value in those finite difference, finite element, yes? Reflectivity methods. Directly in terms of medium properties, get the wave. But there are other times when having this perturbative, if you like, there's some background and then we embed on that differences between that background and the reality. And that difference then, so there's a wave that we associate with the background. And then there's a wave generated by these sources, which are the difference between the reality at that point and the reference. Okay? And that sources can be of several different varieties. They can be what generated the wave. They can be heterogeneities, that medium properties that are not referenced. They can be converted waves. A shear wave that acts as a source of P, yes? A shear source that eventually, yes? All of those are within what we consider source. Okay, so this is saying there are Green's theorem methods for wave separation, Green's theorem for wave prediction. We're going to focus right now on that first, Green's theorem for wave separation, because we're interested in reference wave separating and deghosting. Further today, we're going to talk about Green's theorem for wave prediction, because for migration we need to predict the source and receiver inside a volume, yes? So we're going to have a Green's theorem for that. Then for other applications, we're going to talk about inverse scattering series. So we're on that first bullet right now. So what I said is, there's a useful way to imagine the only commitment we have is that I don't care what your finite difference, reflectivity, this reference and sources, the commitment is you predict a real wave. That's the commitment. How you get there, you use what's convenient for your application. So let's take the simplest case. You have a homogeneous acoustic world, you have a source at R prime, and it produces a field R. And the closest thing we can think of to a point source is a Dirac delta function. And so you have a Dirac delta source at R prime producing a causal field at R. We call that G0 plus of R being the field point, R prime the source. And we are assuming that the source is a single frequency. Yes? It's a single frequency source at a well-located position. We move from that to del squared plus k squared. Instead of G0 plus is Dirac delta, we have del squared plus k squared P is rho, some general source. Could be discrete, could be continuous, could be discrete and continuous. What is rho? We'll give you some examples. Yes? But the main thing is del squared plus k squared is an operator for homogeneity, because k is omega over C0. So there's some kind of homogeneous thing here, and then rho sitting on it, embedded, yes? So this is the solution. If you have del squared plus k squared P is rho, this is the general solution. How do you know? The general causal solution. Operate on both sides by del squared plus k squared. It goes inside the integral. Del squared plus k squared on G0 plus is a Dirac delta, and Dirac delta times rho is rho of R and omega, because you integrate it everywhere. This is one of the cornerstones of math physics for wave propagation. It says, if you want the field anywhere in space, anywhere, you give me the sources everywhere, and I'll give you the field anywhere. There's no boundary conditions, nothing. If you give me the sources, there is no boundary, there is no temporal or spatial boundary conditions. Okay? That, yes. So examples of rho, a minute ago we had del squared plus k squared. Now we have del squared plus omega squared over c squared of r. So this is a wave propagating in a heterogeneous medium. C is no longer C0. It varies from point to point, but we can reformulate 1 over c squared of r as 1 over c0 squared times 1 minus alpha, and put the 1 over c0 squared on one side and the 1 over c0 squared minus alpha to the other side. Is there a pointer? Not? Okay. Okay, no worries. Oh, it's not working?
No, it's here, but it's...
Oh, here we go. Okay, where do you press it? Okay, cool, thank you. So what was on the left-hand side as part of heterogeneity, omega squared over c squared of r, suddenly became omega squared over c0 squared, and then the heterogeneity ended up on the right-hand side, meaning we're back to del squared plus k squared, p is rho. And as soon as it's del squared plus k squared, p is rho, we have the solution, g0 plus rho integrated over everywhere. Yes? So that's an example where rho has two things. Rho has the source that generated the field, and rho is capturing heterogeneity, something that's different between C of R and C0. Yes? Both sources are on the right-hand side, and both are viewed then as generating waves. And we'll give you an equation like that when you integrate. You can also write this del squared plus k squared p in an elastic case, where you could think of elastic whole space, homogeneous, and now you not only have the source that generated the heterogeneities that are involving p, but you have the possibility of a shear wave then gets coupled between ps and then p out and g0 plus. This contributes to p. Yes? So we're seeing the generality, and this is just the beginning. You could have an elastic also as part of the source. All the methods that you're going to see Dr. Xing Wu show for separating the reference wave from the scattered wave, reflection data, and then deghosting, do not care about what rho is. They don't care whether it's just the generator or the heterogeneity or some other field type, yes, entering your field, yes? They are, all they care is there is a source. Okay, so we're back to this equation. Now there's another equation. So this equation is linear superposition. It says this guy is the causal solution to a Dirac delta. This guy has a rho source. It says to get the field due to this kind of distribution of source, at every point r prime, put this weight on it. Put the weight of the actual source there. Yes? And sum. That's just a superposition, and it's an all space solution. Okay? What do I mean all space? It's valid anywhere in space. There's another form, very useful, that has a totally different origin. Its origin comes from Isaac Newton, and it comes from the fundamental theorem of the integral calculus, an absolutely awesome theory. It says, you give me a function, and I take a limit of sum of values of the function times delta x, and I do I make it infinite sum, where the maximum width of the interval goes to 0, and that limit of a sum over this function is replaceable by another function only evaluated at the endpoints. Unbelievable. Think about that, okay? You have a sum of a function, yes? Replaceable by a different function only at the endpoints. That's what the fundamental theorem of integral calculus is saying, yes? And of course it's the antiderivative of the function that you're summing, evaluated at the endpoints. That immediately leads to divergence theorem, which says you have a volume, I have an integral inside a volume, I can replace the integral inside the volume of the divergence by a surface integral, where these guys have the same exact relationship, derivative, yes? And you have Stokes' theorem and so on. This divergence theorem, or Gauss's theorem, leads to this Green's second identity by just substituting A is this vector combination, phi grad psi minus psi grad phi. Please understand, this is entirely mathematics. This is no physics, this is no linearity, this is no causality. That other thing, rho G0 plus, was very much causal and linear superposition, yes? This has an origin where you're not arguing any physics here. That's its power, you'll see, okay? So what you do next, of course, and we've all seen this, is you take this Green's theorem and you put for psi and phi two functions of our interest. One is the actual wave field, and the other is this Green's function for the reference medium, the background we've been talking about, yes? What Green's function? Any Green's function. This relationship here, first of all, when you write it like that, you have not assumed anything about P or del square G, 0. When you substitute del square P and del square G0, their differential equations, now you've gotten personal about what P and G0 are. Here it's just a math identity of any two functions. But once you substitute in for del square P minus K squared P plus rho, and for del squared G0 minus K squared G0 plus delta in here, and here there's a cancellation of the K square P and the K squared G0 terms, and here you end up with the delta. And the delta says delta of r minus r prime. It wants to know in this integral over r prime, is r in the volume? If r is in the volume, you output P. If r is not in the volume, that delta gives you 0. So this term right here ends up with either P or 0, depending on whether r in. So this genius thought, this Green's theorem, because the step before, if you say, well, Weglein seems to be impressed with it, yeah, I'm amazed with this. This is a number. That integral is the area under a curve, yes? Like 7. This is a number equals a number on the bottom. Those are functions of r. Yes, you integrate, you get 7 equals 7. Suddenly a genius, George Green, says, make one of those functions, psi or phi, a function of two variables. Yes? R prime that you're integrating and another variable. Yes? And suddenly these two become functions. Yes? No more just two numbers equal. Yes? That Gauss's theorem would give you. Yes? You understand? This will give you a number there. Yes? So it's very clever. In order to improve upon Green and so on, you have to respect, you know? Okay, so that last result, as I said, gives you for R in the volume, P, if you evaluate R in the volume, and if you evaluate R outside the volume, you get 0. It's not saying that P is 0 outside. It says if you evaluate the right-hand side here, it's discontinuous. Why is it discontinuous? This is discontinuous because of one thing. This guy right here. Why? The normal derivative of the Green's function is discontinuous. Why? Because the second derivative has to be Dirac delta. So the first has to jump. Yes? The Green's function itself can be continuous. The derivative jumps, and that jump here makes this jump, that discontinuity. Inside it's p, outside it's 0. Okay? So this is a theorem. The amazing thing about this is, in deriving this, you never assume that G0 was causal. G0 is any solution of del squared plus k squared G0 is delta. All you assumed is del squared G0 is minus k squared G0 plus delta. That's what you assumed. So any G0 here, causal, anti-causal, anything in between, causal plus anti-causal over 2, any kind of solution you can imagine, and there are an infinite number of solutions to that inhomogeneous differential equation. Any one of those infinite solutions for G0 will produce the causal solution here. That's mind-boggling. Okay? How in the world can, for example, anti-causal, anti-causal, anti-causal produce causal? The reason is you have information here on the boundary. If those values of the field in the normal derivative are actual field values, they will drive this to be a causal solution no matter what the choice is. That is, if you're going to understand migration theory, we need to understand that, because we're going to be predicting causal waves using an anti-causal Green's function. Yes, in migration theory. You understand? It's not you have not violated in the whole space solution. Rho G0 integrate everywhere. You have to have causal. You put anti-causal in there, you will produce an anti-causal Green's function. That surface integral is what this is no longer just an integration over sources. This is a boundary value problem, where boundary information is placed that nails down the causality. Yes? So we have this result, which is for the field inside the volume. And now we have two results. These two results, if you accept them, yes, the one on top called equation 6, the solution everywhere in terms of sources everywhere. The second one's Green's theorem, yes, in terms of an integral only on the volume, and a surface integral on the volume, giving you the field inside. These two equations derive everything in this group. Okay, so if you don't like something in the group, okay, you have to start here with that you don't like, and then tell us you don't like. Okay, if you just don't like it because it's a matter of taste, like I don't like a green tie or something, that's okay. You understand? But if you want to find some issue with some of the methods that we derived that are controversial, we're starting with this. Okay. So what we're going to do, we have this form, that this form, we said, works for any G0. If it works for any G0, let me put in, for certain applications, let's just humor me and put in equation 8 the same G0 that's in 6, which is the causal solution. Choose this G0 here to be the same as here. Here it must be causal. Here it does not have to be. But there's no reason we can't make them equal. Make this G0 the same as that, because we're going to compare. So we have a form. P is an integral rho G0 plus over all space, gives you the field anywhere. So we can break that up. In other words, this result is the integral over the volume, and the integral outside the volume is the same as the integral over everywhere. If this form this plus this is the P anywhere, it certainly also is a solution for R in the volume, because that's part of everywhere. So this plus this gives you the field anywhere, including in the volume. So this plus this will give you the field inside a volume. Now we have another. This on top is only for P for R in the volume. This is valid everywhere, including R in the volume. But for R in the volume, this plus this must be this plus this. What that says is, for R in a volume, this term is this term. Since this plus this must be P for R in the volume, and this plus this must be P for R in the volume, this must be this for R in the volume. What that says is, the contribution to the field P for a point R in the volume due to sources that are outside the volume is this surface integral. This surface integral gives you the contribution due to the sources outside the volume. That's a mind-boggling comment. In other words, a field cares about all the sources. If I say, I'm only interested in the field inside a volume, what it says is, the field says I still care about all the sources. I need to know the sources in the volume if you're confined to interest in the volume. In addition, I need to have a surface integral of values of the field and the normal derivative on the surface, and that surface integral will give you the contribution to an integral outside the volume with sources you don't know. You don't know the sources outside. You compute this integral, it gives you the contribution to this. You know where this comes from? Isaac Newton. Instead of integrating outside, I'm doing something on the surface. Yes? This is the replacement of this volume integral by a surface. Okay? You see how profound that Newton contribution is, yes? To do that integral, I only need to know field and the derivative on the surface. Nothing about sources outside. Yes? Amazing. That is a very famous result in mathematical physics. The fact that if you want the contribution to points R inside a volume due to the sources outside, you do a surface integral. What integral? You do that integral. In Morse and Feshbach, it's in chapter 7. In Born and Wolf, it's on page 100. They call it the Extinction Theorem. Some of you know Ross Hill at Chevron. He did his thesis in physics on that theorem. Yes? So it's a famous theorem that we're talking seismically about. Yes? This is not a new theorem in physics. It's new. Okay. So what does that have to do with seismic? Okay, so here we're going to show two applications. As I said, the reference medium, you can choose to be anything you want. For reference wave separation from reflection data, the reference medium we choose is air and water. That's the reference you're given. What the sources have to do is they have to take that reference that you chose and make reality. Yes? That's what sources have to do. So one source has to be air guns in the water. Yes? The other has to be earth. Yes? There's no earth here. There's water all the way down. Yes? So here you see the sources have two parts. You have to add these two to this picture to get reality, which is air guns, and earth. Yes? And the earth is going to come in as, how do you perturb water to make earth? Yes? Just alpha, beta, perturbations. We don't need to know what they are. All we need to know is there's a source there. Okay? There's an earth down below. So here's the reference Green's function here for that reference medium. And here's the sources. If we perform a surface integral like this, and we evaluate at some point inside this volume, there's a source above the cable, the air guns. So you're going to get the contribution of the air guns to the total field here. Yes? Because the air guns are the only source outside. And that's what the air guns produce in water you're going to get at a point inside the Earth, anywhere. And that was the basis of this paper with Seacrest in 1990, which you can turn that P0 into a wavelet estimator. That had absolutely no value back then. Why? Because there was no data that had the field in the derivative. Okay? Essentially, it was a single cable. Yes? And so the acquisition has evolved. You have geostreamer, you have over under cable. Yes? This is all being revisited because acquisition is where what this needs. So when you have your reference wave and your reflection data today, and you cut that reference wave, you are damaging long offset data by just cutting. This says don't cut, predict. You have the field in the derivative. Predict the reference wave. In a similar way, you can predict the scattered wave. The wave due to the source, just evaluated above the cable. Yes? Okay. So there's an opportunity here. Why? You're collecting long offset data, and yet you're damaging it with that cut of the reference wave. Yes? So that's one application. What about deghosting? We all know what ghosts are. For deghosting, we're going to choose a different reference. The reference for deghosting is going to be a homogeneous whole space. Yes? The whole world is water. Imagine the whole world is water. So now you have three sources. One that has to make this water thing up here air. You need air guns, and you need some source that turn this water into earth. Three sources, yes? A minute ago there were two. Of course you had air and water, so you needed air guns and earth. With this simpler reference, you have a need for another source. So what deghosting is, let's say on the receiver side, you have a receiver, and at that receiver there are some waves that are arriving moving up and some waves that are arriving moving down at the receiver. Receiver deghosting is separating them so you get the wave at the receiver that's moving up. Yes, that's receiver deghosting. Similar on the source side. So how you do that is the following. With this reference and three sources, in other words, if I pick an output point here, in other words, let's say I pick the surface to be this, the cable, and close at infinity, like that. And then I evaluate that at or better yet, make it close on the cable and close above. Yes? Close above. So there's only one source outside the earth. Yes? Whereas if I close this way, two sources are in and one source is out. I want the effect of the source that's out. Yes? That's what the surface integral gives you. So when I evaluate it at this point, R, inside the volume, the earth is producing an up wave. What do you mean up wave? The Green's function in that homogeneous whole space, from any source point, the wave goes out. This is what the Green's function looks like. So this earth is sending out. Air is sending out. Air guns out. At this point, which is above the cable and below the air gun is down, the rho due to air is down, and the rho due to earth is up. So when I get from Green's theorem the contribution at R due to the earth, at this point below the air guns, at that point the earth contribution to the total field here is the only upgoing, yes, because it's below the air guns, yes. So that's the idea. Jingfang Zhang then extended this to the source side, yes. Jingfang Zhang at BP, yes. So this is the source and receiver. Dr. Mayen, who's here, applied on field data, and Yu Chang, Shen, and Zhen Zhang, and Cheng Fu extended this for non-horizontal cable, okay? Okay, so with that too long introduction, maybe we'll take a break for coffee, and then Jingwu will tell us how these, yes? Jingwu will tell us how these Green's theorem methods, the state of them, recent progress for offshore and onshore, both wave separation for reference and scattered, and deghosting. Okay? Why don't we take our coffee break? But you got to promise to come back. Okay? Okay.